In this video, let's enumerate all of the primes up to a given value n. Recall that a prime number is a number that is divisible only by itself and 1. For example, 7 is a prime number because its only factors are 1 and 7, while 8 is not a prime number. 1 and 8 both divide 8, but so do 2 and 4, and because it has more than the factors 1 and itself, 8 is not a prime number. We'll go over one method, which is brute forcing all of the prime numbers up to a number n, and then we'll try to improve and iterate on that before finally going over a mathematical solution to the problem that involves the sieve of Eratosthenes. Let's begin. Suppose that we are given the input that n equals 10. Then we will check the range of numbers from 0 through 9. Notice that we do not include the upper bound, which is 10. We know that 0 and 1 are not prime numbers. 2 is only divisible by 1 and 2, and it is the only even number that is prime. 3 is only divisible by 1 and 3, so it is also prime. 4 is divisible by 2, so it's not prime. 5 is prime. 6 has factors 2 and 3, so it is not. 7 is prime. And then 8 has factors 2 and 4, and 9 has factors 3. Let's code up the simple solution and see if we can improve on it by using some simple algebra. So we have our function signature getPrimes, which takes in a value n. For the purposes of this problem, it's safe to assume that n is greater than 2, as 2 is the smallest prime number and it's not interesting to have n smaller than 2. Let's start by iterating over all of the numbers in our possible range, remembering to exclude our upper bound. Okay, so now we're iterating over all of the numbers, starting from 2 up to n. Notice that we started 2 and not 0 or 1, because 0 and 1 aren't actually prime numbers, and so we won't be using them for the purposes of this problem. Now, when we iterate over all of the numbers, we do want to check if they're prime. If they are prime, we should add them to some sort of output array. So let's create one at the top of our code, and then move further down into the loop to see how we can check how each number is prime. Now we have this array primes at the top of our code, and we'll use this to add our prime numbers to as we come across them. In our while loop, let's figure out a way to check if each value of I is prime or not. To do so, let's iterate again in that while loop, and we'll start at 2 up to our I, and see if any of those numbers divide I evenly. To check this, we can do I mod our new number and see if the remainder is equal to 0. If it is, that means that it's evenly divisible by the number we're at, and in this case, we know that I is not prime. And remember, we're going to start at 2 again and not 1 or 0, because no number is divisible by 0, and all numbers are divisible by 1. So we have our counter variable j, which starts at 2. Our isPrime is a boolean, which keeps track of whether our current number is prime or not. And we start at true. We give the assumption that our number is prime until we find a factor disproving it. Then we iterate from j to I exclusive, making sure not to divide I by itself, and see if I divided by j has a remainder of 0. We use a modulus to check this fact. If I divided by j does have a remainder of 0, that means that j evenly divides I. And therefore, we can set isPrime to false, because that means that there are factors besides 1 and I that divide I. Then we increment j, and once this while loop terminates, isPrime will represent true or false based on whether our value of I is prime or not. That's not all. Let's check isPrime for true or false. If isPrime is true, we'll add I to our primes array, and if not, we'll just continue on to the next iteration of our loop. And either way, we'll have to increment I at the end of this while loop. Great, now we're checking if isPrime, and if isPrime is true, then we'll just append our current I to our primes. And finally, let's increment I. Now, all we have to do at the end of our function is return primes, and we're done with the brute force version of our solution. Now we're done with the brute force version of our getPrime solution. Let's take a look at this and see if we can improve and analyze it. Before we analyze this code, let's see if we can improve the bounds. Our outer loop goes from I equals 2 all the way up to n. There's no way around this because we do have to check all of the primes in this range. However, our inner while loop goes from j equals 2 all the way to I. We can at least improve this to I over 2, and the reason is that the smallest integer that will divide I is 2, besides 1 obviously. And that means that the biggest number that will divide I is I divided by 2. Any number bigger than I divided by 2 will have a factor that is less than 2, and that's not a number that we're interested in. We only care about prime numbers, which are integers. So instead of going from j all the way up to I, let's go from j all the way up to I over 2. We've updated the bounds once, and I've written this in a different color. So now j goes from 2 to I over 2. However, we can improve this a little bit further. Consider the situation where we have I is equal to a perfect square. Then I has some square root, which multiplied by itself has to equal I. Now, if we go to the square root of a number and there's no factor at that point, that means that there must be no other factor for this number, because if we go past the square root of a number or the closest integer square root, then the other factor must be smaller than the square root. For example, for 36, we know that 6 times 6 equals 36. If we look for one factor that is greater than 6, such as 9, the other one must be smaller than 6, such as 4. And because we've iterated over these numbers starting from the smallest to the biggest, we must have already seen one of the factors of this number, and so we only have to go all the way up to square root of I. I've rewritten the bounds now, as j times j is less than I. If we take the square root of both sides, this comes out to j is less than the square root of I, which is what we just discussed. However, the square root function is rather costly to implement, so it's better to write it out this way. Now, we have that j equals 2 all the way up to j equals square root I, and we've improved our bounds a little bit. Let's analyze the complexity of this function. Let's analyze the time complexity of our function. The outer loop goes from I equals 2 all the way to I equals n, which means that it runs in approximately linear time. Our inner while loop runs from j equals 2 all the way up to the square root of I, which runs in approximately the big O of square root n. Then, if we multiply these two together, we get big O of n times the big O of square root n. So we can just add the powers up, and we have big O of n to the 1.5. Our space complexity is fairly straightforward. We have a few integer values and a boolean, which are all constant space. But we also have our primes array, which is approximately linear in its space. So we have big O of n space complexity. Let's see if we can even improve our solution. Our space complexity is linear, and we probably can't do much better because we do not know how many primes are up to a certain number, and so we're going to have to create this array no matter what. Our time complexity is big O of n to the 1.5. It seems like we should be able to improve this to linear time. The intuition there is that if we can see that a number is prime, then we can look at all the numbers that it multiplies into and say that those definitely will not be prime. For example, if we see that 3 is prime, then all of the multiples of 3 following that should not be prime, and we should never look at them again. And if we can do this for all of our numbers, then we'll have a likely better algorithm for finding prime numbers. This is an idea known as the sieve of Eratosthenes. It comes from math, and it's not a super intuitive solution, so an interviewer might not always expect you to come up with it on the spot, especially if you haven't seen it before. However, let's go over it and see how it works. We'll draw an example by hand, and then we'll code it up to see that it's actually a simpler solution than the name might suggest. Let's take the same example from earlier. Suppose that our given n is equal to 10, and we have the range of values from 0 through 9. We'll start off by marking off 0 and 1 as not being prime. Then our next number is 2. Because we've assumed that the remaining numbers are all prime, we'll assume that 2 is prime and mark all of its multiples as not prime, because that means that they're divisible by 2. So we'll skip 2 and mark 4 is not prime, 6 is not prime, and 8 is not prime. Then we'll move on to the next prime number and continue this algorithm. Our next prime number is 3, and we'll go to all the multiples of 3 that haven't already been marked as not prime and mark those as not prime. So here we start at 3 and skip it. We go to 6 and see that it's already marked as not prime, and we'll go to the next multiple, which is 9, and mark that as not prime. Then what's left over are 5 and 7, and because 5 doesn't have any multiple to go to within this range, we're done, and we can finish this problem and output the ones that we found. So the prime numbers we found in this range are 2, 3, 5, and 7, which are exactly correct. So let's see if we can code this up. We'll use some extra arrays, so we'll actually use an array for booleans, which will keep track of which more numbers are marked prime or not, and then we'll still have our output array of prime numbers at the end. Let's start by creating our boolean array. We have an array now called isPrime, and our first step is to set n numbers in isPrime equal to true, and this way we'll keep track of whether they are prime or not. Of course, because we know 0 and 1 will always be false, and we're starting with n is greater than 2, we're going to manually set isPrime of 0 and 1 to false after we complete our for loop. Great, so now our boolean array has 0 and 1 marked as false, and all of the remaining numbers as true, just the way that we did it previously by hand. Our next step is to start iterating over each number and checking if it's prime or not. If it's prime, aka if the Boolean array has it marked as true, let's go over all of its next multiples and mark those numbers as false, because we know that they won't be prime. And if the number in the beginning is not prime because we've already marked it as false, let's just skip it and continue on to the next number. Okay, so far we have the for loop ranging from I equals 0 to n, and we're checking if is prime of I is equal to true, aka have we found a prime number. If so, let's iterate over the remaining numbers or multiples and make sure that we mark them as false. So j starts at I plus I. This is because, for example, if we start at 2 as a prime, we don't want to mark 2 as something that's not prime, we just want to start at every multiple of 2. So we'll start at 2 times I, or I plus I, and then increment by I each time, marking is prime of j equal to false as we go along. Then, once we've exited out of this while loop, we'll just exit out of the if statement as well and iterate over each value of I. If I is not prime, then this if statement is not true, and we won't do anything and we'll just move to the next number. Once this if for loop is complete, we'll have a Boolean array with true marked for all of the prime values and false for all of the values that aren't prime. And then all we have to do is stick this into another array that we will output or return in our function, and then we've completed the function. Now we create the primes array. We iterate over all the values from 0 to n and check if our isPrime Boolean array has that value marked as a prime. If so, we append that value to our primes array, and finally finish off the function by returning primes. Let's analyze the time and space complexity of this function and see if we've done better than our previous one. Let's start with time complexity. We have our first for loop, which runs in linear time. Let's start with our time complexity. Our first for loop is fairly straightforward and goes from 0 to n, so that's linear time. Our second for loop also goes from 0 to n, so the outside is linear time. But the while loop inside is interesting. We know that we only touch that while loop for numbers that are actually prime. So let's go over the first few examples to see if we can find the pattern. We'll go over 2, 3, and 5. So for 2, we'll go over every other number to mark it as prime, which maps to n over 2 numbers. For 3, we'll go over every third number, which maps to n over 3 numbers. And finally, for 5, we'll go over every fifth number, and that maps to n over 5. If we sum up all of the primes over this range, this comes out to log n. I know that's a little bit counterintuitive, and it comes from a mathematic theorem. One way that you can have this intuition is realizing that summing the numbers 1/2, 1/3, and if we include the non-primes such as 1/4, 1/5, 1/6, and so on and so forth, what we have is the harmonic series. And a known summation for that, or approximation, is log n. So if we know that the summation of the harmonic series is log n, we could guess that this inside loop runs for log n iterations. And because we know that the numbers are prime, it runs for log n iterations. Now, of course, this is fairly difficult to derive and probably wouldn't be expected in an interview setting, but because we're able to access Wikipedia and Google right now, we should go over that true fact. So the inside of this loop runs for log n iterations. And finally, we have our last for loop at the end, which runs for O of n iterations, and so we can easily write that in. Then our runtime is bounded by this for loop in the middle, which is big O of n times log of n. And finally, let's do our space complexity. We of course have our integer values, I and j, which use constant space. And then we have isPrime and primes, two Boolean arrays. IsPrime is always size n, and primes is bounded by size n. So if we have big O of 2n, this just comes out to big O of n. And there you have it. Now our time complexity is n log of n, which, believe me, is better than n to the 1.5. And then we have our space complexity, which is big O of n. Now, of course, this is a fairly sophisticated solution to a problem, but it's interesting to go over it because it shows how having a mathematical background can still be helpful in technical interviews. It's important to realize that this is the type of question that, even though it's asked, might not expect you to get this robust solution because there's so much math background involved. However, if you do have it, this will give you the upper edge over another candidate. That's how you enumerate all of the primes up to a given value n.